Hi everyone, it's Peter here from Lucid Motors. As you may be aware, we recently achieved a landmark 520 miles range on an EPA cycle with our Lucid Air Dream Edition. And I really just wanted to take you through some of the technologies that's enabled that and maybe give away one or two little secrets in so doing. So let's start with some science basics. Have I got the energy to get to that position? But a younger, fitter guy than me would be able to run up that hill and get there faster. And interestingly, what's the relationship between that and a horsepower? Well, actually, 1 horsepower, as determined by James Watt many, many years ago, is 746 watts. So a horsepower is about 3/4 of a kilowatt. Very easy math, because that's very close. The 746 is very close to 750. Well, we use a unit of kilowatt hours, and that's the energy that we have in a battery pack. And why we multiply by hours? Because that links power and energy through time. However, the scientific unit for energy is actually a joule, but there's a reason. This apple weighs about 1/10 of a kilogram. It weighs about 1 Newton from Isaac Newton. And if I take this apple and I place it on the floor and I pick it up from about 1 meter to this table and place it on the table, and if I do that in exactly 1 second, I've been exerting a power on that apple of exactly 1. And actually, the math is surprisingly simple, because in the case of our Grand Touring car, we have 112 kilowatt hours, and we also have to remember that joules and watts are linked with seconds. And we actually come to a number which is very close. Unbelievably, I'd have to pick this apple from the floor and put it on the table 400 million times to represent the energy in a full charge of a Lucid Air Grand Touring. It actually came out as the 85 kilowatt hour. Now, we decided to go for these little beauties. And typically, these contain about 17 to almost 18 watt hours of energy each. So we realized we needed of the order of 6,000 of these 21700 cells in order to get a world-class range from the car. Well, the difference is that this truly embodies the space concept. The space concept that really differentiates Lucid Air from the competition, in that the car is smaller and more compact on the outside and bigger and more comfortable on the inside. And you might think, gosh, how have you achieved that? We've achieved this with our in-house drivetrain technology, motor, inverter, transmission, front and rear, super compact, the most volumetrically power-dense system available today. That's where you shouldn't have a tunnel. So this is really a hybrid demonstration model showing the two variants of battery pack that power Lucid Air. We have the foot garage where we delete some cells, and still the car would be capable of over 400 miles in this configuration. But make no mistake, this is more than competitive in the marketplace. We have extraordinary, unsurpassed rear footroom and comfort, even with this version compared with other EVs on the market. It's just that this one here takes it to a whole new level, and I'm really excited. This is the pack that's going to power my passion, the Lucid Air Pure. It contributes to the entire structure of the vehicle. We allow the cells to vent downwards and away from the occupant for safety. Now, also, a key safety feature here of this pack is this ballistic shield, which is 8 millimeters thick, and it is an advanced epoxy composite. But this is not just performing a role of safety, it actually has an efficiency function as well, because this composite undershield is actually curved. So this is where we lead to our modular construction of our battery pack. Many other cars are running at just 400 volts. There's a simple formula for that as well. Power is I squared R. And this is an inescapable law of electrical circuitry. So if we double the voltage, we can halve the current. And if we halve the current, we can quarter the heat losses. There's a little bit of buffer in there with our 924 volts. And, you know, there's no substitute for voltage in terms of efficiency. Now, I want to just put to bed an urban myth about batteries. A lot of people say, well, you can charge so fast because of the high voltage. And it's partly true, but it's super misleading. Bad stuff will happen. If I don't give it that, it won't charge very well. So if the cells don't charge any faster, whether the car's 400 volts or 900 volts, why are you doing the 900 volts? It's the rest of the system. For example, these connectors here on our bus bars are made from aluminum, but there's a cost imperative at work here. Copper actually is the best if you're really limited in space, but in terms of mass effectiveness, weight advantage, I can't see how this results in a higher voltage. So this one will have, that will have 6 volts, and then this one will have 9 volts. Now, can you imagine if this is 9 volts, just how long the flashlight would need to be to achieve 924 volts. So clearly connecting things that way is not the smartest. And also, the way in a flashlight these just touch each other end on end really is not an efficient connection. So we need to think of a different way of doing that. Each one of these is 4.2 volts as an open circuit voltage. To get to 924 volts, we need 4.2 volts, and we need to put 220 of these end on end. So we'd need to think of about a column of these, or a long flashlight. The energy, there wouldn't be the energy in this pack. And that is literally put the cells in parallel. And it's like really, if I were to bunch up a whole group of flashlights and hold them all together, it's like putting them in parallel to connect that way. So here we have the Lucid Air module. And this reveals all the cells on end, 300 of them. And then you can see that the next group of 30 runs through to here. And each of those steps, each group of 30, steps up the voltage by 4.2 volts. That's how a battery engineer would describe the long-range pack of a Lucid Air. So I'd like to just spend a little bit of time showing our cooling strategy here. We use this plate, and this cools the cells from their ends. And it's an excellent way of containing and managing the temperature of the cells. We have to use some of their energy to warm themselves. Well, there's a very interesting aspect of a cell. It is actually able to conduct heat in different directions at different rates. Now, if we take the other approach, which is side cooling of these cells, we have a configuration of cells here in a classic honeycomb, yeah. But we have to make a little gap between them. They won't go right close together because in that configuration, we need to run a coolant channel between them down the sides of the cells. So we won't be able to achieve this close, compact honeycomb that we achieve with Lucid. So here we're able to get more energy more compactly this way, and you tend to get funny tolerancing effects coming in. And as a consequence of that, you tend to get, contact points. I'm not saying it can't be done, but super challenging for a consistent effect. The cell does want to conduct heat, and you can have a really consistent, flat area, but the heat's got to go further, and we've elected for that. And that's part of the reason we're getting this extraordinary efficiency. So our philosophy is to end cool the cells. This gives us a more consistent, more reliable, more manufacturable, more controllable system. And key to that is this cooling plate, this cold plate, which is just a 2-piece aluminum stamping. And what you see are a lot of these dimples here, and these dimples are bonds which hold the lamination of 2 pieces of aluminum together to resist the pressure of the water glycol, which is pumped in and out from these unions. But These dimples provide another function. So why do we want to induce this turbulent effect? We need a fluid which can absorb a lot of heat and collect a lot of heat and transmit a lot of heat very quickly. Now, when we look at the flashlight, we look at the negative being on one end of the cell and the positive on the other. So what we do is we have different gauge bonds for negative and positive. We put a thinner bonding wire here, and we put a thicker bonding wire here. I'm giving away one of our big secrets here. To the best of my knowledge, no one else has done this. But I can give you just a flavor of how vital this management system is. So what we need to do is create this staircase of voltage. And there's 220 steps on the staircase of voltage. What we need to do with our battery management system is iron out and even out that those steps of voltages are equispaced, that we don't achieve an imbalance in the system. And it's been a real pleasure to take this opportunity